Hello, my name is Manaye Unatu. Today I will be presenting the payment drainage and climate resilient chapter. Uh, the outline of the presentation is as follows. Background and scope of the chapter, adjusting hydrological design standards, climate resilience road drainage systems, protection from damage from extreme rainfall, drainage in problem soils, sustainable drainage systems such as climate adaptation strategy, climate resilience drainage in difficult terrains, critical drainage issues in sloping and ground and mountainous terrain. And then finally, I will conclude by summarizing the key points to take away. The failure of the highway payment can often be linked to a poor drainage or drainage system failure. Therefore, before embarking on the payment design, detailed consideration for drainage provision should be made. The purpose of this chapter, therefore, is to provide an overview of a drainage and climate resilience in order to provide a robust payment that will perform its function sustainably. Therefore, this chapter does not cover detailed hydrological and hydraulic design as this can be found in respective country manuals. The existing Overseas Road 31, the fourth edition, contained only 2 pages on drainage, and this has been built upon to include information on how to build in climate resilience through drainage. We now move to the effects of how we shall look at the effects of climate change on pavement design. Road drainage engineers are accustomed to designing road infrastructure for specific type of climate. For example, what pipe diameter is necessary for a culvert to function properly, what asphalt will minimize a pavement life cycle cost, how deep must a bridge foundation be to protect it from scour road, about by coastal storm surge. All of these questions and many others addressed daily by engineers involve assumptions about the climate of the future. Traditionally, the working assumption has been that future climate conditions will be similar to those of the past, and this historical observations is a reliable predictor for what's to come. But the climate that we use to design drainage infrastructure is no longer fixed. Climate is changing, and mm, a basic design based on historical patterns is no longer sufficient. Therefore, information on future climate change needs to be taken into account. That's why the climate hydrological standards needs to be adjusted. Climate is changing in the following way. For example, increased precipitation and flooding, which affects the design of subgrade or cross drainage structures. Less precipitation in some areas and more in others, so it is a variable. Change in the timing of wet and dry seasons, for example, while witnessing summer intense rainfall, sea level rise and associated storm surges affecting our coastal roads, increased river flows due to climate change that significantly affect the design of bridges and bridge abutments. Now, how can we adjust the hydrological standards? Well, there are two approaches that we can adjust the hydrological standards. The option is by taking a precautionary approach, which means adding allowance for climate change, and option two, adjust the standard based on climate change scenarios. Option 1, the precautionary approach is generally recommended for fuel river flows contexts that a single climate change allowance of between 5% to 30% additional flow is applied to the estimated present day, say 100-year peak flow. These allowances are not or projections for rainfall intensity is also between 5 and 30. But these are not forecasts or projections or scenario linked to levels of greenhouse gas emissions. Therefore, recommended precautionary sensitivity ranges for peak rainfall intensities, peak river flows, and sea level are detailed in the following table. For peak rainfall intensity, it is added to a base scenario for immediate scenarios is 5, 10, 20, and 30 from 2090 to 2025, from 25 to 55, from 55 to 85, to 85 to 2115. For sea surface water size, it is 10 centimeter, 15 centimeter, 25 centimeter, 35 centimeter allowance is proposed to be added. Option 2 is just is making adjustment on climate change scenarios based on climate scenarios. The climate projections from selected global circulation model data for short-term, medium, and high-emission scenarios for the climatic variables, which is relative to the baseline scenario over the forecast useful life of the payment drainage system, say, for example, 30 years period. Therefore, similar to the precautionary approach, the short-term, for example, operation and drainage structural fail with shorter design can be taken from the model predicted output 2050 for medium 2080 and for long-term 2021. Problem with the global models is that they cannot be applied in their uh, um, current form without being downscaled. Downscaling general circulation model output to regional scales. Global models are intended for use with large spatial scales and are too coarse to determine local scale climate variations in precipitation. For example, the global model divides the world into little boxes, for example, by 250 kilometer by 250 kilometer, which is by far large compared to a large river basin or catchment basin. Therefore, downscaling is to a regional or local level is required, say increasing the grid resolution to 20 kilometer or further down to a higher resolution 12 kilometer or 2.2 kilometer. Downscaling climate data generates locally relevant climate data from the GSM's global circulation models. Downscaling obtains regional weather phenomena that are influenced, example by local topography, land-sea contrast, and small-scale atmospheric features such as convection. Now we move into external or surface water, surface drainage. Surface drainage is subject is quite widely covered in country manual, hydrology and drainage manuals, and I will be touching it slightly, and our concern is subsurface drainage. Moisture is the single most important factor affecting the long-term performance of a payment, plus also one of the significant challenges in facing payment designers, and the designers must provide the payment structure in which the detrimental effects of moisture are mitigated. Hence, the purpose of the surface drainage is to keep water away from the road. It therefore includes aspects or elements of side ditches, culverts, meter drains, pipes, surfacing, shoulder, road cross section, and to some extent the road alignment itself. um, Water can ingress into the pavement layers through the surfacing because of the oxidative hardening of bituminous layers, cracking of surfaces, joint of modular pavements, cracks in concrete, weakening the top layer, high stress zone areas. And the water can also ingress into the pavement layers through unsealed shoulders. Water easily penetrates and weakens materials below the hull path, which is a high stress zone. An inadequate or low crown height and side ditch invert levels can also cause the water to enter into the pavement layers. These are some example photos. The one you look at in the left is a severely eroded earthen shoulder of concrete road, water can, as you can see here, ingress into the pavement. On the right hand side is slightly better. Limited erosion seen on the shoulder constructed with granular material, and the water can easily flow into the side ditch. There's also another example in rural roads is lack of drainage channel provision or ditch provision, and the grass is growing on the verge of the road, which is obstructing the surface drainage from draining away from the road. So it stands responding on the road and creates deformation or creating low bearing capacity, and water can ingress at this location in here. So it is recommended that ditches be provided and the grasses be regularly cut or trimmed. Prevention of surface water ingress, adequate crown height. Well, these are the measures we need to take to prevent surface water from ingressing into the pavement layers. The first one is adequate crown height and ditch invert level. Prevent ingress of moisture from the pavement edges by sealing the shoulders, raising the embankment. Use impermeable seals such as OTA seals and cap seals. Undertake periodic maintenance. We now move to an internal or subsurface drainage. Despite an efficient and functioning surface drainage system, it is not possible to completely stop the water from entering the pavement layer. This can be a result of infiltration, capillary action, side drains, and through surfacing as discussed earlier in the previous slides. Therefore, subsurface drainage is concerned with the movement of water that enters the road pavement. Here, the diagram here shows a kind of construction arrangement for subsurface drainage. If you have a permeable base as shown in number 3 and you have an impermeable shoulder as shown in number 4, here number 4, and you may always make sure that the shoulder is sealed. This is to prevent boxed in or trapped moisture in the lower pavement layer if water gets through unsealed edges of the shoulder or through the surfacing. Ideally, if you have to use this kind of construction, you have to provide a drainage system as illustrated in number 7 down here. In number 7 here. The best approach to avoid the box-in construction is to use a road base and sub-base that is extended right up to the side drains as illustrated in number 8 here. Please also note that the shoulder is sealed as illustrated in number 2 here. Now, to improve the internal subsurface drainage, the following action should be taken. Avoid boxed-in or trench type construction. Road base and sub base should extend to the side drains as explained earlier. Provide surface drainage systems such as French drains, interceptor drains, filter layers, or drainage blankets and prevent permeability inversion. Now, one of the most climate impact is we are witnessing washout of a pavement on a rural basis quite frequently. A washout is the result of the combination of flood and erosion. So this is a protection from damage from extreme rainfall. Erosion, the other cause for washout can also be related to blocked drains due to poor maintenance as well as inadequate drainage capacity for the extreme event can lead to washouts. Extreme rainfall events can cause washout to occur more frequently as they generally entail a heavy downpour of rain within a short period. Sea level rise will result in coastal flooding being more extreme due to the higher base levels. Increased salinity of coastal river waters with the related impact on salt sensitive structures and increased sedimentation in tidal areas. There are extreme events can cause washout and then inundation. It is the We need to distinguish between inundation and washout in order to select a type of material that we use as a climate resilient measures. Rapid flow of flood water, high current that scours and washes out the pavement structure. This type of mechanism, a pavement type, has very little impact. However, in an inundation where a rise of water that submerges the pavement with no rapid flow or current, then pavement type has an impact, whether it is a bitumen or uh, concrete pavement. Now I'll just show you a video clip which shows a curve being washed out due to extreme event in a real life. Now Kurt is gone and the road in washed out. Here you go. We don't want to be in this situation, so we need to protect our from such scenarios. This is another example of photo which I took in Mozambique. In Chisamo Chiputu section of the road N 220, which was badly damaged by the December 2012, January 2013 flood. As you can see, the road is completely washed out and the culvert thrown out, as you can see it on the right side. This is another example of a road which has been undercutting and the collapse of pavement due to erosion of an embankment. There's another road which is running parallel to the river bank, which has been the river bank eroded, eroding the embankment of the road with it. And this is another road which has been damaged or collapsed in coastal road due to coastal tidal effect. Now, these are some of the extreme event mitigation measures undertake site-specific flood risk assessment because we need to understand the mechanisms of failure in order to provide a workable or sustainable mitigation measure. Early assessment of climate change in the design process is very critical. For example, different disciplines like engineers, climate scientists, hydrologists, geologists, and stakeholders have to work together and not individually. Applying a safety factor, for example, freeboard, is also one measure, considering a long return period for exceptional events when designing hydraulic structures. For example, if you are the design standard is 50 now, we can design it for 1 in 100 year. Using waterproof materials for new designs or treating them to make them waterproof. Reducing the gradient of slopes and taking into account the materials used. Design for future flexibility, for example, leaving extra space for future drainage structures like culvert is also important. A stream bank can be stabilized through the use of gabions, riprap, or increased vegetation. And a soft measure like planning and the design standard is very critical. Increase the resistance of the road structure to erosion, example, through selection of the type of pavement or protection of embankment slopes. Changing the elevation of the road structure, example, increasing or lowering the road elevation is one measure to be considered. And providing cross drainage structures for the road, example, increased size culverts and bridges is also one mitigation measure. Changing the alignment of the road and increasing distance from the river can also be taken as a mitigation measure. For coastal road washout protection measure, constructing levee banks with drainage or seawalls, constructing seawalls offshore or breakwaters, and riprap to protect shorelines from coastal erosion and submersions. Planting artificial reefs and also replacing metal culverts with reinforcement concrete. Resiting of critical infrastructure from areas that are forecast to be most at risk of sea raising sea levels, which is retreating, is also very important. Developing a coastal flood strategy, which is a soft measure that identifies the most appropriate shoreline management plan and assesses whether coastal defenses are required and needed. This is one example. The diagram shows a road being deliberately flooded and with the structural integrity of the road is protected by protection measures. For example, on the upstream side, we can put a dry paved stone over a layer of geotextile or suited filter layers, providing apron stools. And the downstream side, we can construct a concrete and in combination with sealing basin to withstanding water for energy dissipation. This is drainage in problem soils. Building a new roads, especially although drainage in problem soils is a geotechnical issue, drainage has also a vital role to play. Improving the drainage in problem soils is very important. Building new roads, especially on green sites, often requires dealing with problems of-grade soils, some of which occur in most countries. There are various problems of-grade materials, and they need to be addressed individually. For example, expansive soils, collapsible soils, compressible soils, dispersive soils, and corrosive soils. There are traditional remedial measures which include pre-wetting, for example, 2 to 3 months to induce equilibrium moisture content before constructing the pavement. Partially or completely removing the expansive soil, replacing it with non-expansive material, modifying or stabilizing the expansive soil with lime to change its properties, since lime stabilization reduces permeability and both helps to keep moisture out and maintains a high level of strength and stiffness even when saturated. Also, flattening of the side slopes to between 1 in 4 and 1 in 6, depending on the depth of the clay, can also help. Sealing shoulders not less than 1 meter wide is also very important. This diagram shows the zone of moisture equilibrium and so zone of seasonal moisture movements. So the countermeasures, for example, we can flatten the side slope as it can be seen in number 2, and then seal the shoulders and replace clay inert materials as shown in number 4, and then provide lined concrete drains on both sides of the road. Now we move on to sustainable drainage system. The traditional drainage principle is to get rid of water from the road pavement and its surrounding areas with little regard to the damage it causes to the receiving water body or environment, erosion or arable land. It is unfortunately this often results in heightened peak runoff volumes and increases in erosion and pollution problems in natural rivers and streams. Therefore, good road drainage design should consider therefore not just the removal of runoff water, but also maintenance of sensitive environment, public health, and natural water resources, and the effectiveness of future maintenance activities. Sustainable drainage systems designs are drainage solutions that provide an alternative to direct channeling of surface water via lined channels through networks of pipes and sewers to nearby water courses. Therefore, the extent drainage system of road is the approaches to manage surface water that take account of water quantity, which is flooding, water quality, pollution, biodiversity, wildlife, and plants, and amenity are collectively referred to as sustainable drainage systems. Now, there is uh, some now people are becoming very aware of the road, the environment, and the road pollution generated by the road infrastructure. Therefore, there is also legislation being developed by many countries now, and dumping a polluted water is not going to be acceptable. And therefore, it is very critical that the road drainage system to be sustainable. Potential side drainage infrastructures include soils, filter stripes, filter drains, detention basins, ponds, and wetlands, as well as attenuation storages. The main problem with this that these surface water detention ponds can take land intake. Therefore, land is very expensive, and if it is not available within the right hole, it cannot be implemented. But soils and filter stripes, they can be implemented quite easily as they do not take that much land. This is an example of grass soils. People might ask what is the difference between the soil and the traditional grass channel. Well, the soils have here the base permeable layers with huge voids. They can store water and can percolate into the ground, or they can also trap pollutants and improve the water quality. So it has a dual purpose, flood reduction and pollution control. That's seen in here. They can provide scour check at regular interval, and the water can be slowed down, infiltrated, and then the pollutant stop. Therefore, we can make the environment more sustainable and reduce pollution and protect the road from flooding. This is an infiltration basin. Again, it works on the same principle but on a greater scale. So there is, if you look at the cross section here, there is an infiltration material here, the grass, and then the water can be stored, pollutants trap here, and the water, when the peak flow passes, the water can outflow to the next to the downstream water body in a clean water and in a controlled manner. Now we move into climate drainage in difficult terrains. Drainage of road pavements in sloping, flat and low-lying valleys are often poses a problem, and it's a design issue that requires sound guidance for practitioners and road authorities. The following are critical drainage issues needs to be considered in flat and low-lying areas. Quite a considerable amount of information has been included in the updated Road Note 31 guidance document. It is a common for the entire catchment, for example, around the road to be inundated with water during the rainy season. In flat terrain, where obtaining minimum drainage gradient may not be possible, and where water flow at the outlet of a culvert may also be constrained by downstream flow restrictions. Drainage water may also cross private land. This can be a legal issue in some countries, especially if it is an agricultural land. And before the construction of the road in a flat floodplain, the flow is distributed across the land. But when you put an embankment and allow the water to flow through certain location through a culvert, then the water is concentrated in one location. It creates a gully downstream and causes problems. So some sort of distributor needs to be considered. If there are long distances to the natural system, it can also be difficult to remove water fully. So these are some of the mitigation or adaptation measures in flat and low-lying areas include raised formation level of the road, lower the water table by installing longitudinal sub-drains, controlling capillary rise using granular layer, especially if you have a high groundwater level, use of permeable materials like filter mattresses, climate adaptation measures in hilly areas also include controlling seepage flow. Seepage flow is the main problem, erosion protection because of slope, and catch water drains, etc. These are some additional measures in flat and low-lying areas. Once the road is constructed, many of the problems in flat and low-lying areas are quite difficult to solve. Therefore, they need to be concerned, taken into consideration at the initial stages of the design. Good drainage design begins with good road location. Hence, if it is possible, it is important to avoid frequently flooded areas and unnecessary stream crossings. This will greatly reduce cost of maintenance. And if this is not possible, the following countermeasure should be considered. For example, raising the formation level and protecting the embankment with, for example, mortar riprap in the upstream and then a concrete in the downstream along with drainage sealing basin can be helpful. If you have a high ground level or you are passing through swamp areas, capillary control capillary rise using granular layer is very important. For example, the base can be fill material can be rock fill if permanent swamp, and then the granular material could be positioned at least 200 millimeter above the high water level and more than 600 millimeter centimeter below no, greater than 60 centimeter below the sub-base layer. The thickness of the filter layer can be between 150 to 300 millimeter as specified in chapter 4. Therefore, it is very critical to provide to control the capillary rise using granular materials. In critical drainage issues in sloping ground and mountain terrains, upland areas with a significant slope and water course, the type of flooding is very flash, and flooding which occurs over several hours can cause a lot of problem and erosion. As you can see in the photo here, there's a grass sloping ground towards the road, but during a high rainfall, intense rainfall, it has been eroded and debris accumulated on the channel, blocking completely the channel, and then the water flows across the road, which is damaging the pavement. Therefore, I think a catch water drain along with a breastsword and side ditch on both sides of the channel are to be provided to prevent this from happening. And controlling seepage flow using can be protected by using perforated pipe as shown in this diagram. As you can see here, we have a side drain with perforated drain pipes and a cross drainage pipe. Therefore, the original seepage line has been dramatically lowered. When both ground surface and impervious layers are sloping towards the road, seepage flow is likely to reach the road surface. If vertical distance between the surface grade and the seepage level is less than 60 to 90 centimeters, we need to construct subsurface drains to prevent seepage flow from entering the subgrade. Now, whatever we do, unless there is regular and periodic maintenance, the road pavement can prematurely fail. Therefore, adequate road maintenance is the most critical and efficient way of reducing the impact of changing climate on the road system. In the absence of any adequate maintenance regime, the damage caused by climatic event is exacerbated. Thus, maintenance of pavements and sealing activities, regular maintenance of bridges, culverts, and drainage structures to ensure they are functional and not obstructed is very important. Maintenance and improvement of slope protection works and systematic assessment to identify and incrementally address vulnerable and critical road sections are the first defense to climate risks. Now, finally, the key point is to take away highway payments or geometrics, surface drainage, non-payment internal subsurface drainage, climate, and soil properties all have a significant impact on drainage system and then needs to be studied and considered. Consider adjusting hydrological design standards because in order to make your payment more climate resilient. Consider implementation of SARs for climate adaptation to reduce both flood quantity and improve water quality. Special attention is required for drainage of problem soils and difficult terrains. A resilient drainage system with an adequate capacity to cater for increased flows is critical for the integrity and performance of road infrastructure due to extreme rainfall events. It is important for decision makers to appropriately consider and account for extreme weather conditions during the planning, design, and construction phases of the road payment. Avoiding poorly drained areas, unstable foundation soils, frequently free areas, and unnecessary system crossing will greatly reduce the cost of both future maintenance, operation and maintenance. Climate resilience drainage for roads in hilly and mountain areas should also be considered. Thank you for listening.
problem with it.